Energy crisis and climate change are among the biggest problems faced by mankind today. Throughout history, population growth has been supported by a steady growth in energy consumption. However, what happens when these natural resources are depleted? Research has shown that oil production will peak in 10 years' time. Crude oil reserves are vanishing at an astonishing rate of 4 billion tons a year and will be depleted by 2052 at the current rate. The demand for efficient renewable source of energy has never been greater. Wind energy stands out as its contribution to the global energy supply is rising by 25% every year in the past 10 years. However, despite being environmental friendly and cost-free, inefficiency is a major obstacle. Our task is to design, build and test a wind turbine. The design criteria consists of several restrictions. The turbine cannot weigh more than 500 grams or have a diameter greater than 500 millimeters. The turbine can have 1, 2 or 3 blades and must self-start at 10 meters per second. The tip speed ratio must be in the range of 3 to 8 and the maximum angular velocity should not exceed 3000 rpm while rotating in the clockwise direction. Our objective is to achieve maximum power at our design TSR and minimize the mass.
We first selected a TSR value of 4, which is the ratio of blade speed to wind speed. Our goal is to maximize our power coefficient, which is the ratio of power delivered to the turbine to the total power available in the swept area of the blades. To do this, maximizing the area of the rotor disc will allow us to maximize the power in the area swept by the wind turbine rotor. Hence, we chose a rotor diameter of 490 mm with a 10 mm allowance. Although using 2 blades will save on weight, we chose to go ahead with a design of 3 blades as it is more efficient than a 2-blade design of the same weight. A single blade design was not considered due to the complexity of designing a counterweight and the dangers of having an unbalanced wind turbine. Selecting the right aerofoil for the cross-section of our blade is next. We compare the aerofoils by looking at their CLmax, CL/CD ratio, and blade aerofoil geometry. It is necessary to choose an aerofoil with a high CL/CD ratio to maximize rotor torque. Our initial shortlist were these 7 aerofoils. We eliminated aerofoils because their CLmax requires high angles of attack, which is not feasible for our turbine design. The final 3 aerofoils data statistics were compared and SG6043 was chosen due to its advantages in CLmax, geometry, and structural strength. Its CL/CD ratio was the highest of the 3 and stall occurs at a higher angle of attack. Although AH7476 has the highest CLmax, its thin cross-section might be unable to endure the aerodynamic and structural loading during the testing.
In order to achieve maximum rotor torque, a twist must be applied along the span and circulation should be approximately constant. We decided to select the Schmitz model over the Betz model as it is more detailed and sophisticated. Schmitz takes into account the conservation of angular momentum and downstream losses due to the wake. These two methods differ greatly in the optimized chord length near the hub. Using aerofoils SG6043 and a circular root, we created an initial model in Q-blade. We used the programs Schmitz and Betz calculations to create 2 blades for comparison. The Schmitz design blade excelled at CPmax and CT at our optimized TSR of 4 as compared to the Betz design blade, validating our theoretical considerations. Next, MATLAB was used to calculate the optimum chord lengths and the blade twist with the Schmitz model.
The lift ranges from a minimum of 1.3 newtons at the root to 27.5 newtons at the tip. Drag was minimum at the root chord at 0.02 newtons, while maximum drag occurred at the tip at 0.4 newtons. Our wing tip was also chosen to be rounded, as this reduces tip vortices and also makes it easy to manufacture. We then recalibrated our Q-blade design based on this data, and the performance of the new blade exceeded that of the initial blade design. It achieved a CP max of 0.53, which is close to the Betz limit of 0.593. This design also achieved a power output of 104 watts at TSR of 4.1, which is higher than all of our previous designs.
Our blade design was further analysed to look at the structural strength. The stresses on the structure had to be calculated and compared to the given yield strength of the materials used. The critical value for any of these stresses was a yield stress of 21.5 megapascals. The aerodynamic moments, when values of lift and drag are calculated using the theory in a MATLAB script, are shown to be theoretically very low at 3.5 newton meters and unlikely to cause a problem. To calculate the centrifugal forces, the turbine was modelled as a tapered cuboid, thinning towards the end. A maximum stress, therefore, of approximately 1.68 megapascals was found, well below the yield stress. Since the rapid prototyping method only produces designs no longer than 195mm, we split our turbine into two parts. We chose a trapezoidal shaped jigsaw joint with rounded corners to ensure significant interlocking between parts and minimising the stress concentrated on joints. Next, we used a simple half sphere for our cone design to ensure it is streamlined. The cone and the roots of the blade are designed to be printed together to ensure the roots of the blades are strongly attached to the cone. Our hub design should allow the rotor to spin freely whilst being as light as possible. We used only a hub length of 40mm since the loading during testing is exclusively rotational, so a shorter hub will not compromise the performance. A hub diameter of 30mm was chosen for the hub to be as small and as light as possible. The hub is thicker at the three corners where the blades are attached and the stress concentration will be highest. A grub screw will then be used to secure the cone to the hub via a hole drilled at the bottom.
Biologists have always admired the swift maneuver of the humpback whale. It has been suggested that these tubercles function as lift enhancement devices, allowing flow to remain attached for a larger range of angle of attack. The tubercle wing design is a fusion between nature and engineering. The main idea of the tubercles is to accelerate flow as they are forced into a channel, which then creates higher velocity over the wing. Previous studies have also shown that tubercles delay the angle of stall. This might be attributed to the tubercles, which acts as a vortex generator, which then energizes the boundary layer for greater attachment. Adding the tubercles requires us to calculate the optimal wavelength and amplitude of the tubercle spacing. Based on studies, generally the shorter the wavelength, the aerofoil perform better in terms of maximum lift, stall characteristics, and drag. However, this improved performance is bounded by the amplitude of the tubercle. We therefore need to find a compromise between these two factors. Finally, when modeling the wing, we also decided to have a rounded trailing edge due to the limitations of the 3D printer. By having a rounded trailing edge, we are then able to sand it down.
We had to manufacture the aluminium hub by ourselves, and we started with an aluminium cylinder. Using the lathe, we reduced the diameter to 30mm by straight turning. We then drilled a hole along the axis of rotation where the shaft would be inserted. Using the CNC machine, we created the three flat surfaces of the hub. The hub was ready after the keyway is cut using a broach. The blades and nose cone were manufactured using rapid prototyping into two parts, which were later glued and sanded to smoothen the surface and remove excess glue.
We tested our wind turbine in the Donald Campbell wind tunnel. The objective is to derive the maximum power that our wind turbine can generate. Our wind turbine successfully fulfilled the first criteria when it self-started at 7.8 meter per second. To test for power coefficient, the wind turbine is tested at 6 to 12 meter per second and allowed to spin freely until it achieves its maximum RPM. The hysteresis brake is then applied manually until the wind turbine operates at its maximum power. From the results, at the respective maximum power output, our RPM falls safely within the 3000 RPM limit. Overall, our wind turbine achieved a CP value of 0.203, while we exceeded our design TSR by 0.459. Our CP value and maximum power output is lower than our calculations due to the factors such as friction, flow separation, and losses due to the wake. The TSR of the wind turbine may also be affected by design parameters such as the tubercles, which were not accounted in our calculations. We had the opportunity to test a higher resolution model of our turbine in which the tubercles are fine printed. Although the RPM of the turbine is lower, the high-res model produced more power at all wind speeds. This led to a higher CP value of 0.21, proving that the tubercles are indeed effective in power generation. We believe our wind turbine can achieve greater performance through several improvements. In light of the success of our tubercle designs, we will not limit the tubercles to the blade tip, but instead design them on the entire blade. Due to the flaws of the 3D printer, our turbine had small gaps in the blade, and the tubercles are printed differently on each blade. We plan to thicken the blade before manufacturing and progressively sand it down to our desired thickness to ensure there are no gaps. We can cut down the weight of our aluminium hub by drilling holes to improve our power to weight ratio. We can also improve the finish on our blade by applying lacquer to create smoother flow across the blades.